Hello, welcome back to the today class. Today we will talk about some of the illumination, also the shading techniques. You may remember that last time we talked about some of the components of illumination models. We talked about ambient and diffuse, also the specular terms. Today we will talk about how we can put them together as a final illumination model that are commonly used for the OpenGL, which is known as this Phong Illumination. And then we will talk about some of the shading techniques. Also, we will talk about some of the different properties between local, also this global illumination model. I also went over some of your. I actually went over all of your questions, and then I found this question is very interesting. One of your fellow students mentioned that. So last time we talked about some of this Lambert cosine law, right? So basically we know that actually the sum of in this case we got some energy from along the incoming ray, and then we reflect the energy into the outgoing ray, right? And then the sum of the outgoing ray energy should be equal to the incoming ray energy, right? So basically physics tell us that the energy should be conserved, right? I mean the energy should be actually maintained before before we got the energy, also after we distribute the energy, right? But this formula, the last time some of the ambient, diffuse, and this specular term does not maintain that property, since mainly because these are that kind of empirical model. They are not based. They actually these techniques actually based on some of the idea of the physics, but they do not really follow this physical law, right? So basically these formula has that issues. So that's why there has been a lot of advancement along this kind of the illumination model, also this material appearance model. So some of the recent one also maintain this kind of the property. So if you're interested, you can go to my book, and then you can find the chapter about this. Let me show this one. If you go to the book homepage here, then it's not really refined, but actually over there's appearance models. There are also some of these PowerPoint models that explain some of the appearance models. One of the very well known model is actually the facet model. Let me show this one. Microfacet model. So here, if you click this one, I will actually talk about some of the recent one, World BRDF model, also this microfacet model, which is one of the very commonly used model in most of the game and movie. So if you're interested, you can go over them, but actually they are not really refined yet. But anyway, thank you for bringing up these very important issues. And then if you're interested, I recommend you to go over some of the recent materials. So before we move on, I'd like to quickly summarize what we have talked about so far. So basically, in the beginning of this course, we talked about we initiated our discussion based on the visualizing Julia set. Along that application, we talked about some of the basic OpenGL command and structure, like the frame buffer, also this callback function, and then we talked about how we can map from the world coordinate to the screen coordinate, and along that line, we talked about the normalized device coordinate (NDC), and then we talked about the different types of transformations, like Euclidean transformations, also affine transformation. Along that line, we also talked about homogeneous coordinate, which is also related to this projection. And then we define the frames with some of these basis vector. And then we move to the rendering pipeline. Along the rendering pipeline, we deal with a lot of the transformations, like the modeling transformation, viewing transformations. And then along about the modeling transformation, we talked about the dot product or cross product, also discrete rotations. And also we talked about the calling clipping. So we talked to design our these calling clipping operations. We talked about implicit line equations, and we talked about the hierarchical calling to efficiently perform these calling operations. Along this hierarchical calling, we talked about bounding volume hierarchy. And also there we talked about the other calling techniques like the dual frosting calling and backbase calling. And now actually we move to this rasterization based on the edge equations, which is actually related to this implicit line equations. And then we talked about how we can do the color interpolations, this parameter interpolation technique, or also these G-buffering techniques. And now we move to this illumination, how we can compute the color for each vertex of triangle, right? And then we talked about the some of three main, the low-level components like the ambient tone, ideal diffuse tone, also the ideal specular tone. These are actually some of the main components that we talked about so far. Today, we will talk about how we can, we'll move on, we'll continue on our discussion on the illumination model. Now, we'd like to talk about how we can handle these non-ideal reflectors. So the last time we talked about Snell's law, and then Snell's law mainly applied to this ideal specular reflector, right? But if you actually suppose that here, this example, this is normal of the triangle, this incoming light direction, and this R is actually the outgoing, this reflective light direction according to this Snell's law. And then for the ideal specular reflector, basically if our view direction located there along the line with this R vector, then we got all the energy, right? But actually, if we are a little bit away from the R vector, basically our viewing vector away from this R vector, then for the case of ideal reflector, we don't get any energy, right? So that's why actually basically this kind of the ideal reflector applies for this kind of mirror reflection. But most of the actually common objects actually, it's not like the ideal reflector, right? In other words, we can basically when our view direction align with the R vector, we got a lot of energy, right? But when our view direction away from the R vector, we might get a less energy, but we still get the energy, right? And as this viewing vector getting away more from the R vector, we are getting less energy, something like that, right? So in other words, if you're visualizing how much energy this material reflected along this direction, along this ideal the reflection vector, we got a lot of high energy, but energy actually energy kind of gradually going down, right? So a lot of cases actually we are getting this kind of non-ideal reflection, right? So basically, why we got this kind of non-ideal reflection, most of the materials has the roughness, right? So this roughness of surface causes the highlight to spread out, right? And then basically, since there are a lot of this kind of the object in reality, we wanted to. So in other words, the empirical model try to simulate this kind of the effect, this appearance of this effect, without trying to capture the real physics underlying this phenomenon. Some of the recent techniques actually they capture this one based on the real physics law. But here basically we'll talk about some of the early technique of the empirical model to support the non-ideal reflector. So along that line, so this Phong illumination is actually one of the most commonly used illumination model in computer graphics. Basically, this setup is normal and the light direction and this ideal reflection direction, right? And then there should be the viewing direction, right? So basically, our viewing direction located here, and then basically here the main idea is that viewing direction is actually getting. When the viewing direction getting away from the R vector, we are getting less energy, right? So we wanted to simulate that one. How can you do that? So basically we introduced actually the angle between the viewing direction, also the reflection vector, and then basically we used this cosine function. Also there actually we take this exponent of this NS. I will talk about this. I will talk about effect of this exponent later on, and then basically since when the view vector align with R vector, then this turn out to be the maximum value 1, right? So we actually reflected the maximum energy. But this angle getting the angle, in other words, the angle between view vector R vector away getting larger and larger, we are getting less energy, right? So there could be a particular function that describing that one, but we simply use this cosine function, right? The main reason why we are using cosine function is that so basically at high level, as the angle getting wider and wider between the V vector R vector, we should get a less energy, right? And then also we should able to evaluate that function very efficiently, right? And then so along that line with cosine function, and then if you use cosine function, this function can be computed by the dot product between b vector and r vector, right? So that's why the computing this dot function should be much more efficient than the evaluating this cosine function, right? And then this actually and then we also have this the constant factor Ks is the material specific factor for each material. Also there is I is incoming light energy intensity for this non-ideal reflector. So there are sometimes actually when you're performing the dot product between B vector and R vector may have the negative value depending on their angle, but actually these components should be clamped to the between 0 and 1 to avoid any negative value. And then there's this one NS, the specular exponent NS controls how quickly the highlight falls off. Let me show this one. So basically, this is angle between the V and R vector, and then as we get this NS value getting very smaller, like the 0.1, then as the angle getting larger and larger, basically this term actually still maintain and then going down here. But as the NS value very big, like the 10, then this energy actually fall down very quickly as this angle actually getting larger. So based on the NS value, we can actually change the shape of the behavior of how the highlights fall off. So basically, based on this graph, it's a little bit difficult to understand. But let me show you this example. So basically, here we change the light direction. In other words, we change the light direction, right? And then you can see that actually here actually we maintain our viewing direction. But depending on as we change the light direction, you see that the highlight actually changing, right? The way of highlighting actually generates changing. And then also here actually given the same view direction, light direction, we are changing the specular exponent. You can see that here we got the very rough highlight, and then here actually we actually vary very specific highlight, right? And then 1 by bit NS value here. So basically here you can see that a highlight fall off very quickly. So for this one we use this kind of big NS value, and then this one highlight doesn't fall off very quickly, right? So in this case actually we use this kind of very small highlight value. So basically depending on this NS value, we change this highlight behavior. And then basically based on this one, we can actually support the different types of the materials. But again, this is not based on the real physics. So it's a little bit depending on the material, we need to figure it out. What might be the reasonable this constant value Ks, also the NS value. So basically, there's no physical way of computing this NS and Ks value for this different material. We need to try out different value, and then we need to find the reasonable set of the values for supporting a particular actually the materials, like the apple or some of this kind of one, and also some other materials. So this is actually Phong Illumination model, which is actually designed for supporting non-ideal reflector. Which is actually one of the most common these material types. Okay. Also, there are some other one, but actually this was commonly used, so I'd like to talk about this one. So here, even actually, you might remember that we need to actually appear the vector operation to compute this R vector, right? And then here, the Blinn and Torrance this model actually, how they compute it. In this case, they don't need we don't need to compute R vector. Instead, we actually use the halfway vector. Here we define the halfway vector, which is nothing but we sum the L vector, light vector, and the viewing direction vector. Whatever we do, there should be some this viewing direction vector, V vector, right? And then we use the summation of the L vector, V vector, and then here. So basically, if we compute R vector, by measuring the angle between V vector R vector, we actually compute how much highlight we can receive, right? But here we avoid to compute R vector. Instead, we compute the H vector, and at that case, if the V vector aligned under the ideal R vector, then you can see that the halfway vector H vector should be aligned on the normal vector, right? So in other words, in this case, basically we look at the angle between this N vector and H vector. So that's why actually we here in this model they actually they look at the angle between normal vector and halfway vector. So this also the halfway vector also commonly used in some of the illumination model. That's why I wanted to introduce this concept of halfway vector. But here in our class we don't use the halfway vector, but basically this actually summation of the all of components that we talked about so far. This actually ambient term, this is the diffuse term, this is specular term, this Phong Illumination model, the specular term for supporting non-ideal reflector using this NS and also this its own the material, this some of the material dependent constant. This actually we combine these three terms together, and then this actually this model how behave depending on some of the actually their value. Here this one is the light light angle. So in other words, so basically light actually receiving at that direction here, the 60-degree indicating the light actually coming in that direction along the 60-degree, and then you can see that the energy will be reflected a lot along the ideal reflection direction, right? According to this Snell's law, right? But we want to support non-ideal ones. So actually, the energy will be a little bit fall off here, right? The highlight will be actually fall off from this reflection vector. This is actually specular term at that case, and this ambient term, also this diffuse term. The light actually is arriving there, so that actually somehow we receive the energy and we reflect the energy all over the direction as an amount of this energy, right? But here in this case, the light actually arriving from the here. So as you can see, when you're comparing this case, that case, basically ambient term is the same thing, right? So ambient is actually the kind of the background energy, so it doesn't change. It doesn't change, even though we got the different angle of the light incoming direction. But diffuser should change, right? So since the light arriving from our head to there, we receive a lot of energy, so that we can reflect more energy, right? So as a result, we can reflect the energy all of the directions with a more higher amount of energy, right? And here for specular term, since this is the incoming light direction, the ideal outgoing direction that way, right? So that actually we reflect the energy a lot along that direction, and also there are some sort of the fall off, right? And then this ambient term, diffuse, specular, if we put them together, basically this equation tells us that one, and then this actually how we behave, how the energy actually reflected along from here according to the different directions. This is how you can visualize it, these illustrations. So basically this is known as a Phong Illumination model, consisting of diffuse, ambient, diffuse, and this non-ideal reflector materials. If we also visualize this energy with color given this model, this ambient term constant, this diffuse model depending on what angle you receive the light energy, the color changing, and then also depending on our reflector also viewing direction. So there should be some sort of highlight, and if we actually put them together, this is actually the Phong Illumination model, also the Phong reflection model. So it looks very realistic, right? So for example, this kind of Phong Illumination model can support this kind of plastic kind of the material very well, actually. But actually, this is actually empirical model, so there are a lot of issues. What are the coefficient of this copper? I mean, for copper, right? For a particular material, basically we want to compute this kind of the material, right? What are the Ka, Kd, Ks, right? But also for this non-ideal reflection case, what's this Ns, right? but there's actually no systematic way of measuring that this kind of coefficient, right? Mainly because this model is based on the kind of empirical model. It's not really based on the real physics the quantity, right? So basically, they are not the measurable quantity. So we need to try it out. Actually, designer need to try it out different the value. And then for if we wanted to simulate certain kind of the model like the wood, we need to try it out different value and color values, and then we keep doing it, and then we need until we find the set of the value that are that are reasonable, that they can produce reasonable the look of appearance of the wood, right? And then again, basically since this is actually the empirical model, we cannot say that the picture is actually correct in terms, how this our result actually simulate well with the real materials. Also, we can actually say that the energy conserved or not, right? So there are a lot of issues with the empirical model, but early on we adopted this model since basically we can very quickly evaluate these terms. But recent ones, since also the GPU now getting faster, so as a result we can use more the physically based models. Now let's talk about how we can actually use this concept in OpenGL. So light position also they're defined in the world coordinate with homogeneous coordinate. So if you specify the light, also they are transformed by the current model view matrix. And further, the directional light sources, they are actually the directional vector. So actually the homogeneous coordinate will be the 0, right? And then in this case, they are actually vector, not a point. And so the OpenGL, we can use some of these functions, GL light. And then basically, if we can specify this actually the light index of the 0. We specify the position with the light direction, this one, and then here 1, 1, 1, 0. This actually be the directional light. If you want to specify point light source like this, 100, 100, 101, then you can actually put them on here. And also this is how we can set up the light color. Basically, for the ambient diffuse specular, you specify some of the RGB value here, ambient intensity, diffuse intensity, and some other one. So we are showing this. In this slide we didn't show the content of this vector, but this way we can set up the light color. Also, we can set up this material actually the material constant, right? Again, ambient diffuse specular or the shinies. Shinies actually the exponent is the specular exponent. Ambient color, diffuse, specular, and this variable. Basically, here we actually set up the Ka, Kd, Ks, also this Ns, and then if we do that by using OpenGL, we can actually support this kind of rendering. We can have this kind of rendering result. Now I'd like to move on to how we can actually evaluate these illuminations. Early on, this illumination can be very expensive, so we wanted to accelerate this process. So there are actually different ways of applying this illumination model. For example, there could be the triangle faces, vertices, and also the pixel, right? And then sometimes actually we only compute this illumination only for the faces, right? Also, we can also apply this illumination model for each vertex. And then also we can even perform this illumination every pixels, right? Depending on that, there could be the many different shading methods, flat and Gouraud Shading or Phong Shading. Let me show this example here. So here actually we this kind of keep-on model, and then there are some of the triangle here. It's already unclear here. If you look at the slide, you can see that actually we used a lot of this triangle here. And then the flat shading is that we apply our illumination model, in other words, Phong Illumination model for each triangle. So basically when across different triangles we should have a different color. Then you can see that we can get this kind of very clear color change between across these different triangles. So this actually simply is the shading model with this kind of poor quality. So basically, we compute this illumination model. In other words, we evaluate this illumination model, this one, for the center of this triangle, basically we somehow computed the centroid of this triangle, and then we applied this illumination model, and then we use that illumination value across all the pixels within the triangle. Then that's why within the triangle it actually has a flat color, right? That's the same color, so that's why we call this flat shading. Another one is that for each vertex, and obviously it actually gives us a very poor quality, right? Another approach is the Gouraud shading. Is that for each vertex we can have the normal, right? And then based on that we evaluate our illumination model for each vertex, right? And then we interpolate this color that are computed from each vertex, right? And based on this one, we can actually get a more smoother this rasterization result, right? This is known as actually Gouraud shading. But nonetheless, actually you can still see that there are some of the actually you can still see that actually the boundary of the triangle. Another approach is actually Phong shading. Is that basically this is a result of Phong shading. This actually looks better than the prior one here. Its main idea is that so basically for evaluating our illumination model, we need to have this we need to have this different normals, right? And then to do that, also there are many other parameters that actually change when you when we walk along this triangle, right? So to do that, in the case of the normal, here basically we only had a normal for each vertex, right? And then we compute the color here, and then we evaluate the color. We interpolate color. It means that we just use the normal value that are used at each vertex, right? When you are using when you look at when we evaluate this particular pixel, we don't actually change the normal, right? But the Phong shading, we actually we interpolate we starting from the normal at each vertex, and then we interpolate this normal. So here, suppose we want to compute the color here, then we interpolate the normal from then we draw the line here, and then so basically for this one we need to compute the normal here, right? And then for normal here we interpolate these two normal here, and for this one we also interpolate these two normal to there, and then and then from there to normal at the edge we also interpolate these two normal here, right? And then based on this, we can compute the normal at this particular pixel. And then we can actually, also we can evaluate some other one, the light direction and so on. And then we evaluate Phong illuminations with those parameters. So then basically this actually give us this kind of result, and then this can give us the much better result over this Gouraud shading, also obviously much better than this flat shading. But what are the issues of Phong shading? Obviously, we need to compute. It require more computation, right? So it require more time. But with the recent hardware, with the recent GPU, so Phong shading, I mean, obviously this require much computation over this Gouraud shading. But we can actually support this kind of this level of computation. So the Phong shading are very commonly adopted in some of the recent games. And then again, Phong shading results in a very smooth appearance. Yeah, but still along this silhouette, obviously we need to if there are actually less number of triangles, we can see that actually some of the shape of the boundary of triangle, right? So at that cases, even though we use the Phong shading, we might get some artifact. To avoid that kind of artifact, we need to use more triangles. So that's why we talked about the subdivision meshes that we talked about before. Okay, so far we talked about some of the most common illumination model, but all the techniques that I talked about so far, it's kind of more or less local illumination. This local illumination model actually compute the color of the point or surface by considering only a local property. In other words, we only consider position of the point. Suppose that I want to compute color of here, I only consider position of this point, right? And I look at the only surface point property over there, and then property of any light affected, right? So basically, we only look at the data that are locally available, right? So if we do that, if we apply if we only consider that one, we might then if we apply that concept here, we might get this kind of the random result. In other words, no other object in the scene are considered neither as a light blocker, also as a reflector. In other words, in this case, suppose actually there are some of the light behind the above this roof, right? And then there are small window, and then we got the energy that coming from there, right? And then when you come to the color here, then you can see that actually this ceiling actually block the energy, right? But there are small window, and then we got the energy, and then some of the energy passes through the window, and then there are a lot of the energy, right? And then this wall reflecting energy, maybe they're all over the room, across all of the room, right? But in the local illumination, we cannot consider this kind of blocker ceiling. Also, we cannot actually support this kind of the reflector, right? But in the global illumination, actually, we wanted to support this kind of effect. So obviously, if you look at the real physics, in other words, there should be the photon, right? Photon actually they're emitting from the sun, and then a lot of photons passing through this small window, hitting the wall, and then this photon actually interacting with the wall, and then bouncing here and there, and then we can actually observe that energy, right? But somehow this local illumination, in other words, Phong illumination model cannot support this kind of real physics. And then if we want to support the more high quality, we have to simulate that kind of real physics. So in other words, in the real world, the light can take indirect path. In other words, the light reflect off the other materials. Also, light can be blocked by the other object. Light can be scattered, right? Also, light can be focused. Also, light can be even bent, right? And then when we consider the rasterization Phong illumination model, we didn't really talk about these issues, but we need to think about it. We need to have some sort of mechanism to support this kind of one. And then the global illumination, there is a lot of research going on the global illuminations. There are some of the technique. These issues already there are already some of techniques that support this one, while they can be very slow. So for example, for supporting human skin actually translucent model. So in other words, this light can be scattered, right? So we need a way of supporting that kind of one. There are actually a lot of still many open problems. If you're interested, I recommend you to go over those one and think about it, how we can actually support them in an efficient way. So along that line, we will talk about the ray tracing later on. So based on the ray tracing, we can supporting this kind of phenomenon in a rather simple way, but it could be very slow. That's the issues of this low performance of the ray tracing is one of the main issues. But there are a lot of growing research attention on accelerating this kind of global illumination. Okay, so far I talked about the Phong illumination model with some of the shading technique. I briefly talked about the various issues with the local global illuminations. And this is the regular homework. Go over the next lecture slide. Just spend 5 or 10 minutes to going over the next lecture slide. And watch the 2 Specular Asia video and submit your summary before the every Monday class. And submit the question 2 times during the whole semester. So if you haven't done that yet, I recommend you to think about it. What might be you don't need to come up with the very difficult questions. Just write down the question at the Google form. Just write down question that naturally arise to your mind. That's it. Thanks so much. Bye.